Our topic for today is geometric sequences. If you have not already tried this first part on your worksheet that says Explore and has these two tables and then two questions down below, I'd like you to go ahead and try those and make sure you see how it works, and then I'll go through it with you. So pause the video, do what you see here on screen, and then unpause it and I'll go through it. Okay, so our first sequence, we have term number 1, 2, 3, 4, 5, and we just go to the next two terms, 6 and 7. And the pattern that we can see, 3, 5, 7, 9, 11, is that we're going plus 2 at each step. So plus 2, plus 2, plus 2. So to continue on to the next two, we'll get 13 and 15. So this, remember, is called an arithmetic sequence. Arithmetic means we're adding the same thing at each step. So we can kind of characterize that as taking some number of steps forward being repeated addition. So if I wanted to go from a first term of 3 all the way to a seventh term, I know that I'm doing plus 2 at each step. So I'm taking 4 steps forward to go from term 3 to term, sorry, I did term value, but let's just say I want to go, we'll make that a question mark, from 3 to question mark, and we're going from term 1 to term, let's make it something really big, like term 20. So if I'm adding 2 at each step, I'm taking 19 steps forward here. So that means I'm doing plus 2, plus 2, plus 2, plus 2. I'm not going to write them all out, but I would have 19 2's. And conveniently, we have a way of condensing that. If we add something over and over, that's the concept that we think of as multiplication. So instead of writing 2 19 times, I can say 2 times 19, and know that to get to the 20th term, I'm going to be adding 38. So this 20th term in the sequence would be 41, because I'm adding 2 19 times. But literally, that just means plus 2, plus 2, plus 2, plus 2, 19 total times. So this second sequence here also has term numbers 1, 2, 3, 4, 5, and then we would go to 6 and 7. And then our pattern goes 3 to 6, so we added 3. Then we go from 6 to 12, so we added 6, and then 12 to 24, so we added 12. So we're not following a pattern of adding the same number each time. But we are still following a pattern. Here, this would be doubling and doubling. So these are all times 2. So we're doing times 2 at each of these steps instead of plus 2. So we'd go 24, 48, then 96. And then 96 times 2 would be 180 plus 12. So that's 192. So we still have a predictable pattern, but it's based on multiplying a certain number of times instead of adding a certain number of times. So this is what's called a geometric sequence. And it works just like arithmetic, but instead of repeated addition, we're doing repeated multiplication. So to go, let's use an analogous thing to what we did here. So we'll go from 3 to something. And I'm going to pick smaller numbers here. I'm going to say we're going from term 1 to term, I'm going to pick one that's even on our list, term 1 to term 6. So that means I need to do 3 times 2 times 2 times 2 times 2, so that we have 5 steps, right? From 1 to 6 is 5 steps. So I need to multiply by 2 5 times. So that would be 3 times 2 is 6, times 2 is 12, times 2 is 24, times 2 is 48, times 2 is 96. So we come up with 96 by doing times 2 at each step. And conveniently in math, we also have a shortcut for repeated multiplication. Do you remember what it is when we multiply by the same number over and over again? So for here, we went from addition to multiplication. And here we go from multiplication to exponents. So if we multiply 3 times 2, 1, 2, 3, 4, 5 times, that's the same as saying 3 times 2 to the 5th power. So just like a bunch of addition steps become a multiplication, a bunch of multiplication steps become an exponent. So this we can write as 3 times 2 to the 5th, and we can do basically the same idea as over here. If I wanted to go all the way from step 1 to term 1 to term 20, that's a total of 19 steps forward. So I would have done 3 times 2 to the 19th power. And that would be an absolutely enormous number. It would get very, very big. But if I wanted to find term number 20, that's how I would do that. So we found our next 2 terms, and we see how they're alike and different in that they're a repeated operation, but the repetition here is addition, which repeating it turns into multiplication. And here we're repeating multiplication, which turns into a exponential. So here they talk about the recursive rule for these two. If you remember the recursive rule for arithmetic sequences, we said that some term, the next term in the sequence, is always going to be the term before the previous term, so an minus 1. So remember, if we're looking for term 5, then it's term 4 plus our common difference. So we can find any term by adding that common difference to the term before. And we have a similar recursive rule for geometric. It says any term is the term before it, so an minus 1, times our common ratio. So this common factor that we're multiplying by, so up here we were multiplying by 2 at each step, so that would make r equal to 2. And we were adding 2 at each step for the arithmetic, so that made our common difference equal to 2. So the way we would write the recursive rule for that one up above would be an equals an minus 1 times 2, because that's our common ratio. So I guess it does tell us to do that here. Sorry, I missed it. So write sequence 1 using a recursive rule. So that would have been our next term equals our previous term plus 2. And then our geometric sequence would be the next term equals the previous term times 2. So very similar looking, except that the way we get from one term to the next in arithmetic is by addition, and the way we get from one term to the next in geometric is by multiplication. Otherwise, these function very similarly, and you'll see a lot of commonalities between what you learned about arithmetic sequences and what we're going to do with geometric sequences. All right, so we're going to graph both of these. Go ahead and try to do that on your paper if you haven't already. So pause the video, graph these two, and then unpause it, and I'll go through it with you. Okay, so sequence 1, we started at term 1. We had a value of 3, so that's a little bit down here below 5, so below, so 3 would be actually a little above toward 5. Let's see, I didn't realize we were counting by 5s, I thought we were counting by 10s. So let's make our first point just a little below 5 here. And then when we added 2, our second term was 5. Our third term was 7, so a little bit above 5. And then at 4, we went to 9, just below 10. And 5, we're just above 10 at 11. So if we connect those, we get a nice straight line because we have a slope of 2. We're adding 2 at every step. Let's switch over to an orange color here, and we're going to graph the geometric sequence. So we started at 3. At step 2, we doubled that, so we're up to 6, so just above 5. Then we doubled that at step 3, we're up to 12, so that's about here, halfway from 10 to 15. And then we doubled that 12 and got 24, so at step 4, we're almost up to 25. And at step 5, we doubled 24 and we're all the way up to 48. So that's 48 right about there. So notice that this is not a straight line, right? This curves up and it increases much more quickly than the arithmetic sequence. So we see that by repeated multiplication, our numbers grow a lot faster. So the growth pattern, the important thing here is geometric grows much faster. Or in the case of a downward slope, it would shrink much faster as well. Wherever it's headed, it's going to get there a lot more quickly than the arithmetic one. So arithmetic is linear, and geometric is nonlinear, and like we said, the rate of change is very different between the two. Okay, so sequence is I guess a predictable pattern. I don't know actually exactly what goes in here. If you want to look at the answer key on Canvas, you can. I'm just going to put in my definition. It's a predictable pattern. Yeah, that's fine. An arithmetic sequence is a pattern of repeated addition. So the really key thing here is that we're adding something over and over. So we have that common difference. Oh yeah, the difference is called the common difference. Good. Common difference, which we call D in those formulas up above. A geometric sequence is pretty much the same, but it's a pattern of repeated multiplication. And then the ratio, the thing that we're multiplying by at each step, is called the common ratio. And we used R to represent that. All right, so we're going to look at these sequences and try to determine whether they are arithmetic, geometric, or neither. So number one, actually try these yourself if you can. So you understand the rules of these two now. You should be able to answer these two. Or these six. So pause the video, try to answer 1 through 6 here, and determine are these arithmetic, geometric, or neither, and also try to figure out the common difference or common ratio if they are one of our sequences. Okay, so we have 3, 8, 13, 18, 23. This is going to be arithmetic, and our common difference is going to be 5, because we're adding 5 at each step. 1, 2, 4, 8, 16. So that's 1 times 2 times 2 times 2 times 2. So this is going to be a geometric sequence, and our common ratio is 2. Next one we have 24, 12, 6, 3. So that's half, 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 half. So this is geometric. And the thing we're multiplying by at each step, remember this is like dividing by 2, but dividing by 2 as a multiplication, we would call that the common ratio is 1/2. So multiplying by 1/2 and dividing by 2 are the same exact thing. Okay, next we have 55, 51, 47, 43. So we're doing minus 4, minus 4, minus 4, minus 4. So this is arithmetic. And our common difference is going to be a -4 because we're taking away 4 at each step. And just like over here, subtraction, repeated subtraction, is just adding a negative number. Next we have 2, 5, 10, 17. So that's not multiplying by anything in common. It's adding 3, adding 5, adding 7. So this is neither arithmetic nor geometric, even though it is predictable. So we add +3, +5, +7. So I know actually if we follow that pattern, the next term is going to be +9, then +11, and so on. So it's predictable, but not one of our two special kinds that we're talking about. And number 6, finally, we have +3, +5, +7, +9, +11. So that's actually that same exact pattern, but that's neither arithmetic nor geometric. Okay, so our formulas, these are what we call the explicit formulas. So if you want to add that as a reminder from what we did on arithmetic, these are explicit formulas for these sequences. The way we derive it is to say that any term number n, so if we want basically term 35, then n is 35. It's going to be always based on the first term, and we're going to add our common difference times n minus 1. So basically, just like we did up on the very first table, what we're doing there is taking the first term and adding the number of steps we're taking times the common difference. So let's go back and see, because I know it looks more complicated when it's in that format, but all we're doing there is this. We're saying that if we want to know term number 20, we're going to do the first term 3 plus the number of steps from 1 to 20, which is 19, times the amount we added each step, which was our common difference of 2. So this is plugging in numbers to that explicit formula. So hopefully that helps it make sense a little better. So this is the general format of it, but I know it's harder to look at with AN, A1, ND, all of those things. So all we're really saying here is take the first term, the number of steps you want to take forward, times the common difference. So if you want to go 50 steps forward, then you do 50. So from term 1 to 51, you would do 50 times that common difference. Our explicit formula for a geometric sequence is almost identical. We're doing, if we want to find out any term, we take the first term and we multiply by, so remember common difference here, we're adding. Common ratio here, we're multiplying by our common ratio raised to the power of the number of steps we want to take forward. So if we wanted to go from term 1 to term 20, we're taking 19 steps forward, so there would be a 19 right here. 20 minus 1 would give us 19. So same idea, we add some number of common difference times, or we multiply by our common ratio to an exponent. So it's like common difference upgraded to multiplication, and common ratio multiplication upgraded to exponents. If you forget that, just kind of always remember you can go back and think about it the way we talked about here, where you're looking at it in a table and thinking of taking individual steps forward by adding and doing that a certain number of times, or by multiplying and doing that a certain number of times, which becomes an exponent. Okay, so for these we're going to find the first 6 terms and state whether it's arithmetic or geometric and what is the difference or ratio. So first one, let's see, we have 4 of these, so I'll go ahead and go through 2, and then if you can pause and go through the other 2, that'll be good. So we have AN equals 3n plus 2. So the plus tells us this is an arithmetic sequence, and we know that our general form was AN equals A1 plus our common difference times n minus 1. So the part that has multiplication happening, that's where our common difference is. So 3 is going to be our common difference because that's where the multiplication is occurring. And if we want to find our terms, we can plug in term values. So 1, 2, 3, 4, 5, 6. Term number 1, if I plug in 1 for n, that would be 3 times 1 plus 2. That would give us 5. And if I plug in 2, 3 times 2 is 6, plus 2 is 8. And remember, our common difference is 3, so we should see adding 3 at every step. So we'll go from there to 11, and then 14, 17, and our last step should be 20. So let's double check. If we plug in 6 for n, 3 times 6 is 18, plus 2 gives us our 20. So that should be good. All right, number 2, we have 3 times 2 to the n. So since our operation that's happening between our terms is a multiplication, not an addition, this is a geometric sequence. So that our first term is going to be, let's plug in 1 for n. 2 to the first power is 2, times 3 is 6. So our first term is 6. Our second term is 2 squared, so 2 to the second power is 4, times 3 is going to be 12. And then, since our common ratio here is 2, that's the thing being raised to the exponent, we should be multiplying by 2 at every step. So when we plug in 3, that's going to be an exponent of 3, so 2 to the third power. Remember, that's the same as 2 times 2 times 2, which is 2 times 2 is 4 times 2 is 8. So 3 times 2 to the third, or 3 times 8, would be 24. 2 to the fourth, 2 times 2 times 2 times 2 is going to be 16, and 3 times 16 is 48. So that's our fourth term. And then you can see that our pattern is holding, right? Times 2 times 2 times 2, so then we have 96 and 192. So that's how our pattern is working. We're multiplying by 2 at each step. But remember, any single one of these, we could go back and plug in 6 here, and that would just be 3 times 2 6 times. 1, 2, 3, 4, 5, 6. And that would give us the value of 192 if we multiplied all that out. Okay, so try numbers 3 and 4 on your own. Make sure you see how these are working, and then I'll go through them. So pause the video, try number 3 and 4, and then unpause when you're ready. All right, so let's just go ahead and make our list. 1, 2, 3, 4, 5, 6. Our first term here, 3 to the first power is 3 times 2 gives us 6. So very similar to the last one, right? We had a first term of 6. The difference is, now when we go to the second power, that's 2 times 3 times 3. Before it was 3 times 2 times 2. So 3 times 3 is 9, times 2 is 18. So instead of doubling, we're tripling the value at each step. So our next step is 30 plus 24 is 54. Then tripling that, we get 150 plus 12 is 162. Tripling that, we get 300 plus 18, so that's 486. And then tripling that one, we should get 1, 2, and then 24, so that's 1, 4, and then we have a 4 left over, and then 18, so 1458, I think. If I got that wrong, I apologize. These numbers are getting big for doing in our heads. But that should be the right idea, right, is that we're tripling at each step, times 3 times 3. So notice that when the base, the thing we're multiplying by, or our common ratio, is 3 instead of 2, even though these two looked almost identical, 3 times 2 to the n, 2 times 3 to the n, look how much bigger this one got. So in number 2, we went from 6, and in 5 steps forward, we got up to 192. In 5 steps forward here, we got up to almost 10 times that, 1,458. So a larger base or a larger common ratio makes your sequence grow or shrink very, very fast if it's a much bigger or much smaller number. Also notice that geometric sequences grow way faster than arithmetic. So we took 6 steps forward here by adding 3 at each step, and we only got to 20. Here, when we multiplied at each step, so I guess these two are similar, right? It started at 2, and we were here multiplying by 3 and here adding 3. We got to 20 in 5 steps, and here we got to 1,458. So it grows way, way faster, and we saw that back on our graph right here. This linear function is growing nice and slow, and the geometric is growing rapidly and grows faster and faster the further you go. Okay, so number 4, we have a 5n minus 1. So our first term, if we plug in 1, would be 5 minus 1. That would be 4. 1, 2, 3, 4, 5, 6. And then if we plug in 2, we'd have 10 minus 1. That's 9. And we're adding 5 at each step. Our common difference in front of our n there is 5. So we'll go 4, 9, 14, 19, 24, 29. And if we want to go back and check, plug in 6 here. 5 times 6 is 30, minus 1 gives us 29. All right, so these are nothing new. You should be able to do 1 through 4 here on your own. They're exactly the same stuff that we've been doing. So the only difference is they're having you write the equation. So I'll look at 1 or 2 of these with you before we move on. So here we have plus 3, plus 3, plus 3, plus 3. So the first number in the sequence is a 3. The common difference is plus 3. So our equation, remember if we're going to write it in explicit form, it always looks like an equals our first term plus our common difference, so d, times n minus 1. If we know that our first term is 3 and our common difference is 3, that would be an equals 3 plus 3 times n minus 1. So we could use that as the equation. We also, if you recall, have a thing we called a simplified explicit equation, and that's actually what we were working with in the last 4 problems. Notice none of these had an n minus 1, they were just n. And we can get to simplified explicit in 2 different ways. We could distribute, so I can distribute this 3 here to the n and the minus 1, and that would give me an equals 3 plus 3n minus 3. And then I can cancel out these 3 and negative 3, and my simplified explicit is simply an equals 3n. The other way that we can get to our simplified explicit formula, if you recall, is to go backwards in the series and find the 0th term. So let me cover over this one here. So our sequence starts at 3, and if we wanted to go to the 0th term, so go back 1 term, we would be subtracting 3, and that would be term value of 0. So term 0 has a value of 0 here, meaning our formula would be an equals 0 plus our common difference times n. And we use n instead of n minus 1 because we were starting from term 0, not term 1. So this would give us the same result, an equals 3n. And that's the other way of arriving at that simplified explicit, is by starting with the 0th term instead of the first term. Let's look at that for a geometric problem as well. So here we have times 2 times 2 times 2, and that means that our first term is 4, our common ratio is 2, and we could write our explicit formula as an equals our first term of 4, and then since we have a common ratio, that means we're multiplying by our common ratio raised to the power of n minus 1. So that's our explicit, but then simplified explicit, we could do back to the 0 term. So if I go back 1 term, I would be dividing by 2, so this would be 2. And that would mean my simplified explicit formula from that would be an equals my 0th term, 2, plus my common difference, 2 to the n power. So that's the other way of arriving at that. So an equals 2 plus 2 to the n would be our simplified version. And if you want to double check that, if we plug in 1 for n, that would be 2 plus 2 to the first power. So 2 plus 2 is 4. That's our first term. If we plug in 2 for n, 2 squared is 4 plus, oh, sorry, this is times. That's the problem. When we're doing geometric, we're not adding at each step, we're multiplying. So this, I apologize, was 2 times 2 to the n. So when we plug in 2, we get 2 squared is 4, times 2 is 8. Plug in 3, 2 to the third power is 8, times 2 gives us 16, and so on. So this is basically our simplified explicit formula. All right, I'll let you try number 3 and 4 on your own. I'm not going to fill those in because they work exactly like what we did on 1 and 2. So try those 2 out. Remember that you can either start from your explicit formula or use the 0th term and write the simplified explicit formula immediately. Okay, so now we have recursive formulas. So explicit formulas are the nice one where we can just plug in a term number and get a term value. So we can plug in n and find out what a certain term is. The recursive formula worked a little differently because it has 2 parts. It tells us what is term number 1, and then it tells us the rule about the common difference or the common ratio. But this rule says that we need to know the previous term in the sequence to find the next term. So we can't just plug in any value for n here unless we know all of the terms leading up to the one that we want. So this one, remember, is not as useful, but we do need to know how to read it to find the information. So we want to know that it tells us term number 1, and it tells us our common difference, which is the same information that we had in the explicit formula. It's just written a different way. So let's go through these, and then the geometric is the same. We need to know term number 1, and then we need to say what is our common ratio that we're multiplying the previous term by. Okay, so number 1 here, we have -4, -6, -8. We're subtracting 2 at each step, meaning it's an arithmetic sequence. Our 0th term would have been -2, so my explicit formula could simply be an equals my 0th term, -2, plus, since this is arithmetic, we're adding. Our common difference is -2, so I'm actually going to change this to -2 times n. So -2 minus 2n is our simplified explicit formula. Our recursive formula has 2 parts, so we usually show it with the curly bracket like that to sandwich them together. So term number 1, or a1, equals -4. And then any term is the term before it. So remember, this never changes, it's always the same. And the only piece we care about out of this is our common difference, which is a -2. So that tells us our first term is -4, our common difference is -2. Explicit and recursive will work the same way for geometric. This is another arithmetic though, so I'll let you have number 2 just as practice on your own. Let's look at number 3. This one is geometric because we have times 3 times 3, so we're multiplying by 3 at each step. Our 0th term actually would be very ugly here because it would be 25 over 3. So let's write our explicit in terms of term number 1 and say an equals our first term, 25, times our common ratio, which is 3, to the n minus 1 power. Our recursive, we're going to say the first term is 25. And then our any term is the previous term, an minus 1, times our common ratio of 3 raised to, or times 3, right? We don't have any exponents here because we're just saying whatever the previous term is times 3 gives us the next term. So again, the recursive formula, we can't just plug in an n value like we can here. So if I wanted to know term 17, I could say it's 25 times 3 to the 16th power, 17 minus 1. But if I wanted to know the 17th term here, I don't have a way of figuring that out unless I know the 16th term, because it says it's the 16th term times 3. But if I don't know the 16th term, I can't really do anything with that. So that's why it's important for us to remember we can turn this formula into this one by just rearranging the format. So let's actually do that on this one. Instead of writing the explicit directly, let's use the recursive and see how we change one to the other. So here we have times 3 times 3 times 3 again, so that's geometric. Our recursive formula, a1 is 3, and any term is the previous term times 3. So if I want to change that into explicit, the 2 important pieces of information are term number 1 and the common ratio. So to write the explicit formula, we always put an equals term 1, which is 3, times, since this is geometric, we're advancing by multiplying, and then our common ratio, which is 3, raised to the n minus 1 power. So that's how we change recursive into explicit, is by taking term 1 and the common ratio and just plugging them in here. The rest of what's around it is always the same. Okay, so the last part of this is some word problems. I'll let you work through this page on your own as practice. The key will be on Canvas, so hopefully you'll be able to work your way through those using the stuff that we've talked about. Remember, the big takeaway here is we have 2 kinds of sequences, arithmetic and geometric. We advance in arithmetic sequences by adding repeatedly, which is like multiplying, and we advance in a geometric sequence by multiplying repeatedly, which is like raising that common ratio to a certain power of how many steps we want to take forward. So this is the start. Tomorrow we'll do some more practice on this, but do the practice that you have and try to get this down.